Tossing of a coin. Consider the tossing of a coin which has probability 1/2 of landing on either one of its two faces. Focus attention on this coin after any toss. Part A. What is the mean number of tosses of the coin before the next appearance of a head? So, what is the probability of getting a head after capital N tosses? Because for each toss the probability of getting a head is 1/2. So let's say that we get a tail with a probability of 1/2. So we should have gotten tails n times, and then we will get a head. So 1/2 to the power capital N. So what is the mean number of tosses before the next appearance of a head? So the number of tosses from 0 to infinity, the number of tosses capital N times the probability of getting a head after n tosses, 1/2 to the power n. So this is basically the definition of the mean number. The mean number of tosses of the coin before the next appearance of a head is sum over all possible values of n multiplied by the probability of getting n. So if you plug in the numbers here, this gives us n equals 0, and then n equals 1, we obtain 1/2, n equals 2, we obtain 2/4, n equals 3, we obtain 3/8, n equals 4, we obtain 4/16, n equals 5, 5/32, etc. This gives us 1 plus, so these two add up to 1, 0.37, 0.25, 0.15, etc. And this sum adds up to 2. Or it basically converges to 2. Or we can say that the probability of getting a head each time is 1/2. So in every 2 tosses, on average, we expect a head. So because the probability is 1/2, so on average, in every 2 tosses, we expect a head. So we can reach this result. All right, so our answer to part A is 2. What is the mean number of tosses of the coin since the preceding appearance of a head? The result that we obtain here is independent of the history of events. So n bar is still 2. So the question was, what is the mean number of tosses of the coin since the preceding appearance of a head? So we shouldn't get a head. The result is independent of the history of events, so n bar is equal to 2. Suppose that a head has just been obtained in the preceding toss. How would the answer to part A be affected by this information? It is unaffected for the same reason. All right. So we're doing an experiment, tossing of a coin. When you toss a coin, there's a probability of 1/2 of landing on either one of its two faces. We're neglecting the probability of getting a side landing. So we focus attention on this coin after any toss. So we want to know the mean number of tosses of the coin before the next appearance of a head. So the probability of getting a head after capital N tosses is, because for each toss the probability is 1/2, 1/2 to the power capital N. So you should have gotten 1/2 probability a tail capital N minus 1 times, and then with 1/2 probability you get a head the nth time, so this becomes 1/2 to the power capital N. So when you multiply all the probabilities, what is the mean value of n? Well, it is the sum over all possible values of n equals 0 to infinity, and multiplied with the probability of getting a head after n tosses, 1/2 to the power n. It's the definition of the mean value. The variable multiplied by its probability of occurrence is summed over all possible values, and this gives us 2. So we obtain an infinite series which converges to 2. Or we can say that the probability of getting a head is 1/2, so in every 2 tosses on average we expect a head. Part B asked us what is the mean number of tosses of the coin since the preceding appearance of a head. So a head just appeared. Now what is the mean number of tosses after that in which you will get a head again? The result is independent of these two events, so n bar is still is equal to 2. If a head has just been obtained in the preceding toss, the answer to part A is unaffected because these are statistically independent events. The result of the experiment is independent of the past.